So 9.2 beta, we'll start with the Google Slides. And that's true. You should memorize. You should memorize what? Sine, cosine, and e to the x. Okay, it's on the PDF. I'll point that out to you. Now, sine and cosine aren't that big a deal. Why? Because you know by association that cosine is an even function. And the expansions, even exponents, even power functions, and even factorials in denominator. And the sign is odd. And you use odd exponents, odd power functions, and odd integers in the denominator. And we'll do e to the x. So again, this thing, what's missing? Maclaurin. Maclaurin means it's centered about 0. There's no shift left or right. H is 0. What the textbook calls A, x take away A, is your H that you learned in pre-calc. H units to the right, K units up and down. That's the same thing. And what's missing here? What's missing is x to the 0, anything to 0 power is 1, over 0 factorial, which is also 1. And f prime of 0 over 1 factorial. Well, by putting them in there, it helps you recognize the pattern. It's harder to see that pattern without those zeros in there. So just take the derivatives. Yes. Then what? You put zeros in there. And those blue numbers are the coefficients of the x terms. So you got a 1 and a 1, the blue ones. 2 is over 2 factorial. See, 1 is over 0 factorial. That 1 is over 1 factorial. 2, 3 factorial over itself, 4 factorial over itself. Well, what happened? We already knew what that was. See, that's geometric. And this is 1, first term, divided by 1, subtract the constant multiplier. So you have 1 times x times x squared times x. That's how we started this in 9.1. So all you did is say, well, we know what that answer with that expansion is going to look like, and we're just going to use the algorithm to take us to the same place. So you need to look up there and make sense, that screen makes sense to you. I'm not really worried about long division. You get the same thing. I don't think people are really very good at long division. If I divide the denominator into the numerator, ready? You divide the leading terms. 1 goes into 1 once. 1 times this is that. You subtract it, and then you're just repeating it, and that's what's going to take you. But you're not really going to have to worry about long division. That's not going to be something you're strong at. So we're back here. Except now it's what? It's 1 divided by 1 plus x. Which means your constant multiplier is what? Everyone. Luke. Negative x. Ready? This is first term. 1, subtract the constant multiplier. If you have plus x, you subtracted a negative x. So that would be 1 Subtract x plus x squared, subtract x to the third, yes. But if you use the algorithm, look what you would get. Same thing. They're just showing you can get there from here. See, that's geometric. The cosine and the sine and e to the x are not geometric. You have to use the expansion. This, you could use the expansion, or you could just multiply by the constant ratio, which you have to interpret from the function. So they're just confirming that this will work, even though you don't really need it, because we know what that is. It's the first term divided by 1, subtract the constant multiplier. Transcendental functions mean that they cannot be expressed as polynomials, like sine and cosine are transcendental. So here's cosine. But what? They're going to use the same technique. Cosine, there are the derivatives. Here are the values at 0, which every time for sine and cosine are going to be 4 outputs, and then they're going to repeat themselves. So what did they do? They took these outputs and posted them in blue underneath that. And there's where you get the cosine. And what do you notice of the cosine? This is 1 times x to the 0 over 0 factorial. 0 is an even number. You're using the cosine, the graph of the cosine is an even function, meaning it's symmetrical about a reflection over the y-axis. And the expansion's even power series. The sine is an odd function. It's symmetrical about a rotation of 180 degrees. And you use odd exponents in the expansion of the sine. Now you can do the sine this way, ready? You can do it. But you don't have to. Why not? Because you could take the cosine and take the opposite of the derivative. Because the derivative of cosine is negative sine. So you just get the opposite. It's going to take you to the same place. Now, this is more intuitive. Like, well, how do you know to do that? You need some practice, but it's just substitution. It's 1 subtract, first term divided by 1 subtract the constant multiplier. The constant multiplier is x squared. Oh, now what? This goes back to chapter 3. Chapter 3, section 8, when I said the derivatives of the inverse trig functions, you have to match them. So if you're trying to anti-differentiate this, you have to recognize this is a pretty user-friendly question if you can match it. If you can't, you're trying to anti-differentiate this. 1 over 1 plus x squared dx, where mu equals 1 plus x squared, d mu dx equals 2x, so d mu equals 2x dx, and you cannot introduce a variable. So this problem cannot be anti-differentiated by substitution. So when you see that, you have to make an association in your mind. You're not giving me a dead-end problem. What do I match that with? You match that this is the derivative of inverse tan. I wouldn't memorize inverse tan. I would just say, you're going to have to be able to match it. Now, do you understand what's happening here? You've got a 2 over 3 factorial. It happens in all of them. What does 3 factorial mean? 3 times 2 times 1. Ready? And this 2 is reducing with the 2. So you'd have 1 times 3, which is a 3. No factorial anymore. This is just a little bit of algebra going from this line to this line. That's where those factorials went, because they reduce with what's in the numerator. In this numerator, you got 3 factorial. Well, 3 factorial over 4 factorial, everything from 3 less will reduce. So it just leaves you that 4. No more factorial. So e to the x, it's its own derivative. We're just going to get 1s. Okay? So, we don't want that. What's this view that I'm trying to get rid of? All right. So here's the ones you memorize. E to the x, which you just saw, sine x, cosine x, and this geometric. This is from the old school topic sheets, which is they preceded the units. So College Board published these topic sheets going back years, and they wrote them on there. The fact that they're not on the units doesn't mean you're not accountable for them. Meaning, you could do that. You could derive it during the test. And if you're doing that, it's going to slow you down to the point where you're not going to get through the questions you need to get through. It's not that complicated. You're memorizing 3 of them, and you're just recognizing that this one's geometric. Okay? So we're telling you this. We're telling you the value of the function, the first derivative, the second derivative, and the third derivative. What does that polynomial look like? So we'll pause this. Okay, so that's 60 seconds. You got those values? What are we doing? They're telling us this. We put these in the expansion. So I put it so it fit in one line. Those are zeros. Leading coefficient for the derivative is 1. Then 2. Okay? Except what? That's got to go over, ready? 1 factorial, that's got to go over 3 factorial, and you would have x plus x to the third over 3. Okay, so if we went over that too fast, it's on the PDF. You come back to it. It was a. Now, so I put this together, like just organize things. Series could be arithmetic. They could be power series. Geometric series are subsets of power series. They could be Taylor. Maclaurin are subset of Taylor. Most of them are neither. But that's how this all fits together. Okay, we're not interested in arithmetic series. They're not getting us anywhere. Because in arithmetic series, you're adding the same amount. That's not going to converge. We want series that will converge. So we're concerned with the center of this. So here's exploration 2. What are they doing? In exploration 2, they're saying to you, find the sign expansion and differentiate that to get the cosine. So here's the sine expansion. You note it? Now what have you got? X to the first over 1 factorial. These are odd powers. When you differentiate these term by term, since the derivative of the sine is cosine, you're getting the expansion of even powers. Ready? 3, take the derivative of this. 3x squared over 3 factorial. The 3's reduce. It leaves you with x squared over 2 factorial. Well, I don't need the factorial, right? Because it's 2. I can just leave the number 2. Yeah. Except what? The 2 factorial helps you see the pattern. So, example 3. What are we doing? Here's the Maclaurin series. And again, we just wrote it all out. We're saying f of 0, the function at 0, over 0 factorial times x caret 0 is going to begin to give us the power series that will estimate the function. The derivative at 0 over 1 factorial times x to the first. First derivative, first power. Second derivative, second power. That's Maclaurin. For a Taylor series, we're shifting it. H units to the right, up k. So I just said, y take away k, replace our zeros with h's. Now, the book's not going to write h, they're going to write a's. Doesn't matter what letter you use. So the Taylor series, wherever this thing is centered, that's your h. You shifted it, I don't know, 3 units to the right. Then your a or your h is 3. You want the derivative at that value over 0 factorial times x, take away that value, caret 0, and just expand it.